Last day to drop the course is today,
Okay, I'm out.
but without getting refund, right? Okay, I will give you the quiz at the beginning today, but you have to turn in the quiz on Monday. So on Monday, please turn in problem 37 in section 10.3 and problem 29 from section 10.4. And the reason I'm doing that is because I need the class time to go over some lecture materials. So here's the quiz. You're going to it's a take-home quiz. Bring it back on Monday. You have to show if you just write down a final answer, you will get no credit at all. You have to show all the steps, all the work, in order to get credit. Okay. The first one is a graphing problem. The second one is finding area problem. So once again, 37 and 29, those are the ones that you need to bring on Monday. Okay, so I'll now continue with the lecture from section 10.1. 11.1. I think last time we looked at the sequence R to the n, where R is a constant, and last time we figured out that the sequence R to the n has limit 0 when R is between -1 up to +1, and the limit is exactly 1 when R is 1, right? So again, the limit of R to the n is 0 when R is between -1 and 1, excluding -1 and 1. And the limit is 1 when R is exactly 1. And for other values of R, the sequence R to the n is divergent. The sequence R to the n is divergent for other values of R. Everybody is clear? It is convergent when R is between -1 and 1, excluding -1, including +1. Is that clear? That's the recap of what we did last time. Any questions on that? You guys remember that we did that last time? Okay. Today, we want to look at another topic about sequence. A sequence, remember, you have seen increasing, decreasing functions in Calc 1, right? Here we are going to talk about when a sequence is increasing and decreasing. So a sequence is increasing. What does it mean to say that? A sequence is increasing. It means that the next term of the sequence is always bigger than the previous term. The next term is always bigger. So that's what it means to say that a sequence is increasing. So if you think about it this way, think about the graph of the sequence as dots in the plane, right? If you walk on the dots, you are going higher and higher. The sequence is increasing. The way we write it is that the sequence AN is called increasing if the nth term is always smaller than the next term, the n plus first term. So the n plus first term is bigger than nth term always, for all n. In other words, what you have is that A1 is less than A2, A2 is less than A3, A3 is less than A4, and so on. Everybody's okay? So the sequence is increasing means the next term is always bigger. And a sequence is decreasing if the next term is always smaller than the previous term. It means that if the nth term is always bigger than the n plus first term for any n. So the sequence an is decreasing if the nth term is bigger than n plus first term for any n. In other words, what it means is that when you have a decreasing sequence, when you have a decreasing, so an is decreasing, it means that A1 is bigger than A2, is bigger than A3. So that means the next term is always smaller. Everybody's okay? So if you walk on the graph of the sequence, you're always going down, right? Okay, any questions on this definition? Anyone? Okay. So we are going to call a sequence a monotonic sequence if it is either increasing or it is decreasing. Everybody's okay? A sequence is called a monotonic sequence if it is either increasing or it is decreasing. A sequence is called bounded above if you can find a number capital M such that every single term of the sequence is less than capital M. Okay? So a sequence is bounded above if the nth term an is less than capital M for all n. Okay? Is everybody okay with that? So this capital M is called the upper bound of the sequence. Capital M is called the upper bound of the sequence. Similarly, a sequence is called bounded from below if you can find a number lowercase m such that every single term of the sequence is bigger than lowercase m. So a sequence an is bounded below if there is a number lowercase m such that the nth term an is bigger than m for every n. Okay, is that making sense? Every single term is bigger than lowercase m. And lowercase m is called the lower bound for the sequence. Am I making sense? And when we have a sequence which is bounded above and bounded below, that's called a bounded sequence. If you have a sequence which is bounded above and bounded below, that is, if you have a sequence that has an upper bound and a lower bound, it is called a bounded sequence. Is everyone okay with what I just said? For example, suppose that I have the sequence an, which is the sequence -1 to the exponent n. And this is for any n larger than or equal to 1. Can someone give me an upper bound for an? What would be an upper bound for an? Infinity is not a number. Upper bound is 1, right? Because every single term is less than or equal to 1, right? Every single term of the sequence is less than or equal to 1. What would be a lower bound? Yeah, very good. So lower bound, why did I say bounded? Okay, so upper bound and lower bound. So lower bound is negative 1 because every single term is larger than negative 1. Let's look at another example. Let's say now I have an, which is just n. Okay. So what would be an upper bound? Let me just say BD. And what would be a lower bound? What's an upper bound and what's the lower bound in this case? Again, the sequence for, let's say, n larger than or equal to 1. Lower bound would be 1, very clearly, right? And upper bound? What's that? None, right? No upper bound. You cannot give me a number such that every term is less than 1, right? So we don't have any upper bound in this case. Let's look at another example. Let's say an is n over n plus 1. In this case, what's the upper bound? Upper bound. And what's the lower bound? What would be the upper bound, yeah? Why? Yes. Yes, the upper bound would be 1 because note that this is a ratio, right? So, and in that ratio, the numerator is smaller. The numerator is smaller than the denominator, right? So no matter what n you plug in, the numerator is always smaller than the denominator, so the ratio is always smaller than 1. So that's why the upper bound is 1. How about the lower bound? Yeah, you could say 1/2, but you could also say, so once you have once you have one upper bound, right? Let's say you found out that the upper bound is 1. Well, then I can say 1.1 is also an upper bound. I can say 2 is an upper bound as well, right? Once you find the lower bound, right? For example, in the first example here, we found that the lower bound is -1, right? Once I find I have a lower bound -1, then anything smaller than that is also a lower bound. So -2 is a lower bound. -1.5 is a lower bound. You guys see that? Everybody's clear on what we mean by upper bounds and lower bounds. If a sequence has an upper bound, it has infinitely many upper bounds, right? Because if you find an upper bound, then anything bigger is an upper bound. If a sequence has a lower bound, it has infinitely many lower bounds, because anything smaller than, once you find a lower bound, anything smaller would be a lower bound. Everybody's okay with that? All right, so let's go back to the slides again. We have gone through that. Okay, so now remember this. Some people, I mean, you would suspect that if you have a bounded sequence, remember bounded means you have an upper bound and a lower bound, right? So when we say that a sequence is bounded, what do we mean by that? So remember that an is bounded means there exist two numbers. There exist two numbers, lowercase m, uppercase m, such that every term is between m. Every term is between lowercase m and capital M for all n. So a sequence is bounded means that every single term is between the lower bound and the upper bound. Okay? So notice that if you have a bounded sequence, you would suspect that it is a convergent sequence. However, that's not always true. For example, you looked at the sequence -1 to the n, right? -1 to the n, that sequence is what? -1, +1, -1, +1, right? -1, +1, -1, +1. That's a bounded sequence, however, it's not convergent, right? However, if we add another condition, then we can make a bounded sequence convergent. So if I have a bounded monotonic sequence, the sequence must be convergent. Okay? If I have a bounded sequence and if I have a bounded monotonic sequence, it is going to be convergent. Is that making sense? Remember, monotonic means it's either increasing or it's decreasing, right? So here's the picture. Let's say you have an increasing sequence, and the sequence has an upper bound, capital N. Okay? Suppose you have a bounded increasing sequence. You have an increasing sequence bounded above. Okay? Then it has to converge. If you have an upper bound, remember I said, if you have one upper bound, you know that there are many upper bounds, right? Now, if you pick the least upper bound, you have many upper bounds, right? You can obtain the least one, the least upper bound. That's what L is. And that one is the limit of this increasing sequence. Am I making sense? An increasing bounded sequence converges to the least upper bound. Is that making sense? An increasing bounded sequence converges to the least upper bound. You guys understand what I mean by the least upper bound? You look at all the upper bounds, what's the smallest one? That's the least upper bound. Can someone tell me the opposite? What if you have a decreasing sequence and it is bounded below? What's the limit? What's the limit in that case? Greatest lower bound, right? You have a decreasing sequence bounded below, so it has lots of lower bounds, right? Which one should you pick? You shouldn't pick the largest, you shouldn't pick the smallest, right? You should be picking the greatest lower bound. Am I making sense? Everybody's okay with that? All right, so this is called the monotonic sequence theorem. Every bounded monotonic sequence is convergent. You have to remember that fact. We're going to use that later. Every bounded monotonic sequence is a convergent sequence. And I have already talked about the rest on this slide. Any questions on what I said so far? Any questions? Okay. Did I send you the slides? Okay. I think I did. Yes. Check your email if you didn't see that yet. I think we are done with this section, which means that you should start doing your homework from this section. Make sure that you get done with those problems by Monday, because if you don't understand how to do these problems in section 11.1, you're going to have you're going to have harder time to understand the material in 11.2. So please make sure that you go over all the problems in 11.1. Okay, so what I'm going to do is move into section 11.2 now. And that's where we start talking about series. And this is one of my favorite topic as a student in calculus courses. This is probably this is the only part that I enjoyed in calculus. Maybe you wouldn't feel the same way, but one of the things, though, there are so many things. These things are very simple, I think. However, simple doesn't mean it's easy. These things are simple, but then there are so many definitions and there are so many different ideas that if you don't work hard and read through the material and do the problems, it's pretty easy to be lost.
So it's kind of like English language.
Right. Right. So here's so series. What is a series? Okay. We have seen what is a sequence, right? A sequence is an infinite list of numbers, and if you add all the terms of a sequence, you get an expression like this, right? You get an expression which is an infinite sum, right? A1 plus A2 plus A3 plus dot 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 AN plus dot dot dot. It means you're adding all the terms of the sequence AN, okay? And this expression is called a series or infinite series. We are going to use this summation notation to express this infinite series in an abbreviated way. Okay? So this symbol here says you're taking the sum of AN as n varies from 1 up to infinity. Right? So this symbol simply means this expression here. Okay, notice that when n is 1, you get when you plug in 1 for n here, you get the first term. When you plug in n equals to 2, here you get the second term, and so on. Everybody understands that symbol. Okay. How many of you think that you have never seen a series before? How many of you have seen series before? In a calculus class? Okay, most of you didn't see series before, but I bet you have seen an example of a series before. So here's what I'm saying. All of you must be familiar with the following. Let's say I have the number 0.1111. 1 is repeating. Notice that this number is the same as 0.1 plus 0.01 plus 0.001 plus 0.0001. Do you see that? So the number 0.1111 is, I can express it as an infinite sum, right? Everybody realizes that? Okay, so you have really seen this, but it's just that not the way we are going to look at it now. So that's what a series is, right? Okay. Let's look at two examples. The first example is the sequence given by n, like the nth term an is n. So the sequence is 1, 2, 3, 4, 5, 6, and so on. That's the sequence I'm looking at, and I want to add all the terms of that sequence. So what do I get? I get this expression here, right? The question is, does this expression make sense? Does this expression make sense? And the answer is no, because as you add more and more terms of the sum, right? If I add the first term, I get 1. If I add the first 2 terms, I get 3. If I add the first 3 terms, I get 6. If I add the first 4 terms, I get 10, right? And so on. Notice that as I add more and more terms, the sum is getting bigger and bigger, right? Am I making sense? The more terms I add, the bigger sum I get. It's not really approaching a specific number. Am I making sense? So this sum should not make sense. Okay. On the other hand, let's look at this the second example. Oh, did I forget to do that again? Okay. Let's look at the second example. In the second example, what's the sequence? The sequence is powers of half. Powers of half. So in the second example, I have a sequence where the nth term is given by half to the power n. Okay? So here's what I'm saying. Here's what I'm saying. So in the second example, my sequence an is half to the n. In other words, I have 1 over 2 to the n. That's the sequence that I have in the second example. So what's the first term? Half, 1/4, 1/8. Oh, sorry, no plus yet. 1/8, 1 over 16th, right? 1 over 32, and so on. So that's the sequence we are looking at in this example. So if I add the terms of that sequence, I get this sum here, right? If I add the terms of that sequence, I get this infinite sum. Let's see, does this sum make sense? Well, if I add the first term, I get just half. If I add the first two terms, I get 3/4. If I add the first three terms, I get 7/8, right? If I add the first four terms, I get what? 15/16, right? And so on. In fact, if I add the first n terms, I'm going to obtain 1 minus 1 over 2 to the n. Is that making sense? If I add the first n terms, I get 1 minus 1 over 2 to the n. Now, because I have a formula for the sum of the first n terms, now I can answer the following question. As n gets bigger and bigger, the sum is approaching what? 1, because 1 over 2 to the n is going to 0. So, as n gets bigger and bigger, it means that I'm adding more and more terms, right? You guys realize that? As n gets bigger and bigger, I'm adding more and more terms, and I'm saying that the sum is getting closer and closer to 1, right? So, in this case, it seems like this sum should have a meaning. And the meaning of this infinite sum should be 1. Right? Everybody realizes that? So how do I sort of define when is a series, when does a series make sense, when does it not make sense? When is a series convergent, when is it not convergent? So here's the definition. Well, we have talked about this. Suppose that I have a sequence, and the sequence is A1, A2, A3, A4, A5, and so on. That's the sequence. So if I add up all the terms of the sequence, I get the series. And I'm going to define what I call partial sums. So I'm going to define S1 to be the sum of the first term. S2 would be the sum of the first two terms. S3 will be the sum of the first three terms. S4, sum of the first four terms. And so on. What is Sn then? Sn, generally, that's the sum of the first n terms. And I can express this sum with summation notation as the sum of ai, where I varies from 1 up to n, right? I can express this sum in this way. Everybody's okay with that? So this is called the nth partial sum. This is called the nth partial sum. So notice that I have this sequence of partial sums, right? S1, S2, S3, S4, S5. This is the sequence of partial sums. What's the meaning of these partial sums? It's basically I'm adding more and more terms, right? Right? So if the sequence of partial sums converges to a number, then the infinite series should have that sum, right? Am I making sense? if the sequence of partial sums converge to a number, then the sum of the series should be the limit of the partial sums. Is that making sense to you, that the limit of the partial sums should be the sum of the infinite series? Because partial sums are doing what? It's just adding more and more terms, right? The next partial sum is always adding one more term, right? The next partial sum is always adding one more term. So if the partial sums converge to a number, if the partial sums, the sequence of partial sums has a limit, then that limit should be the sum of the series. Okay? So the definition is the following. What do we mean by the sum of a series? Suppose I have a sequence A1 through A1, A2, A3, and so on. The corresponding series is the series A1 plus A2 plus A3 plus dot dot dot. And Sn is the nth partial sum. So Sn is A1 plus A2 plus dot 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 An. And if the sequence of partial sums is convergent and the limit of the partial sums is S, then we say that the series is a convergent series and the sum of the series is S. In other words, the sum of a series is equal to the limit of the partial sums. The sum of a series is the limit of its partial sums. Is that making sense to you? The sum of a series, is the limit of its partial sums. So that's what we have. When the limit of the partial sums exists, we say that the series is convergent. If the limit of the partial sums does not exist, we say that the series is divergent. Everybody's okay? Any questions? Yeah. Well, S is the limit of the partial sum, so it's going to depend on what series you have. I'm going to give you some examples in a second, and you'll see what we mean by that. So let's actually do some examples right now. So let's go back to the example that we saw. Let's say I have the sequence AN, which is given by just n, and n is larger or equal to 1. So if I add up the terms of this sequence, I get what? I get the series A1 plus A2 plus A3 plus dot 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 plus AN plus dot dot dot. So what is this sum in this case? It's 1 plus what? 1 plus 2 plus 3 plus dot 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 plus n plus dot dot dot, right? That's the series I have. What I want to know is this series convergent or divergent, right? So what I want to do is, hey, what's the nth partial sum? The nth partial sum is 1 plus 2 plus 3 plus dot 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 plus n. This is the nth partial sum, right? You're adding the first n terms. Anyone remembers what is? Do you remember a formula for this sum from Calc 1? Has anyone taken Calc 1 from me here? Well, you better didn't. Okay, because I talked about this formula, yes. N into, so this would be equal to n times n plus 1 divided by 2. So if you add 1 up to n, you get n into n plus 1 over 2. That's the formula for adding up the numbers up to n, the positive integers up to n. Everybody is okay with that? So this is the nth partial sum. So now let's look at the limit as n goes to infinity of the nth partial sum. Well, that's going to be the limit as n going to infinity of n times n plus 1 divided by 2. And what is that limit? It should be pretty obvious. Yeah, the limit is infinity. I mean, it's not a number, right? So we say that this series is divergent. The series 1 plus 2 plus 3 plus dot 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 plus n plus dot 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 is divergent. It doesn't have a sum. This series doesn't have a sum. Everybody's okay with that?
So how do you get the formula?
I didn't show you how I obtained that formula. I'm just giving you the fact that the sum is that. Okay. If you are interested to know how one can prove that the sum is this, I can show you that after the class. Okay. But yes, I didn't really show you how I obtained that formula. Any other questions? Okay, so let's look at a different example. Let's look at a different example. Let me first see what example do I have in my notes. Okay, so here's another example. Let's say I have the following sequence. An is half to the n, and I am going to assume that n is larger or equal to 0. So I'm going to start at 0, if that's okay. It doesn't really matter whether I start at 0 or not. No, actually, let's just start at 1, just to make it the same as what I had in my slides. Okay. So let's say this is what I have. So what's the corresponding series? 1/2 plus 1/2 squared plus 1/2 cubed plus dot 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 1/2 to the n plus dot dot dot. So that's the series that I have in this case. Now, what is the nth partial sum? The nth partial sum is half plus half squared plus half cubed plus dot 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 plus half to the n. That's the nth partial sum, right? And what do I have to do? I have to find the limit of the nth partial sum, right? And if the limit exists, then that's the sum of the series. If the limit doesn't exist, then the series does not have a sum, right? Everybody's okay? But how do I find the limit of this nth partial sum? Well, there is a trick to it. It's not a usual trick. What we are going to do is so this equation that I have now, I am going to multiply both sides by half. So notice that if I multiply both sides by half, I get half Sn is equal to what? What do I get? 1/2 squared plus 1/2 what? Third 1/2 to the fourth plus dot dot dot. At some point, what is the term previous to that? What's the second last term? Half to the n minus 1. So when you multiply that by half, you are going to get half to the n. And then when you multiply the last term, by half, you're going to get 1/2 to the n plus 1, right? You guys agree with that? I should have written I should have written this half squared below the half squared here, okay? Everybody's okay that if I multiply both sides by half, that's what I'm going to get. The sum will go from half squared up to half to the n plus 1 if you multiply each term by half. You guys realize that? Now notice what happens when I subtract Sn minus half Sn. So on the left hand side I'm going to get Sn minus half Sn. What do I get on the right hand side? What do I get on the right hand side? Anyone? What's that? Yeah, top minus the bottom, and what is that equal to? Anyone sees? Yeah. 1/2 and 1/2 and y plus. I'm subtracting, right? What's that? 1/2. See, notice that these terms will all cancel out, right? Up to n, all the terms will be vanishing because you're subtracting, right? So you're going to have half from the first row, and then you're going to have negative half to the n plus 1 from the second row, right? Because half to the n plus 1 will not be canceled out by anything from the first row, right? You guys agree with that? If I subtract, this is what I get. Now notice, now on the left hand side I have 1 minus a half times Sn if I factor out Sn. And here I'm just going to keep, let's see, here, here I'm just going to write it as half, doesn't really matter, half times 1 minus half to the n. Just factor out a half. And then what do I have for Sn? Sn is then half times 1 minus half to the n divided by 1 minus a half. You guys agree with that? Are we all okay with what I have here with the algebra? Questions on that? Now notice that 1 minus a half is just what? So this thing here cancels out the half here, right? And so what is Sn then? 1 minus half to the n. Remember, this is what I said before, right? In my slides I didn't show you that. And so what is the limit as n going to infinity of Sn? That limit is what? 1, right? Because half to the n will go to 0, right? And so the limit is 1. So our conclusion is that the series that we had, half plus half squared plus dot 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 plus half to the n plus dot dot dot, this infinite series is convergent and the sum is 1. Everybody is okay with what I said? Please read through the slides, look at the video if you need to, make sure you understand all the definitions, these problems that I did, and we are going to continue from this next time. Yeah.